Today we're going to have a look at the equilibrium constants prep and just have a look at a couple of common mistakes and little bits like that, as well as the mark scheme. So question one, you're given a bit of background. You've got methanol and carbon monoxide making ethanoic acid, and you've got to put your equilibrium constant. You can see that at the top here. A couple of things, we did have a couple of people writing with square brackets. That would be for a Kc, the concentrations. We're using the pressures, so it should be the pressure of each of those substances. Part two, we've then got to calculate the partial pressures. We know that the total pressure is 32, and at equilibrium the partial pressure is 22.2 of the ethanoic acid. Now, since the methanol and carbon monoxide react in a 1-to-1 ratio, and since they also start with the same number of moles, then their pressures must be equal at equilibrium. So if we take the 22.2 away from the 32, you get a 9.8, and then divide that by 2, and you get your 4.9 for each of them. But that's because they've got a 1-to-1 ratio and they were starting with the same amounts, so their change must have been equal, and then we can subtract out what the resulting pressure from the ethanoic acid is. Can then calculate our Kp value. It's basically just inserting everything in, and to get our final answer, you would units, you would have atmospheres on the top and atmospheres squared on the bottom, so we can cancel that, and then to bring that back above the line, we would write it as atmospheres to the -1. We've then got another sample, and we're filling in the table. And you can see, for again, very similar idea. It says 93.6 of the methanol was converted, so we work out what's left, i.e. that final 6.4%, and 6.4% of 50 is 3.2. So that's all you've got to do there. And if you've then worked out what you've got left, or you work out what that 93.6% was, 93.6% of 50 is 46.8, and again it's all reacting in a 1-to-1 ratio, and so we get that all the same. Substitute that in and into the equation to calculate the partial pressure. So we've got the number of moles divided by the total number of moles times the partial pressure, and we get 28.2. The reaction exo or endothermic, explain your answer, comes up next. When we're explaining our answer, you need a reason why. So those of you that just wrote exothermic, there isn't an explanation there. So it's exothermic because the reaction moved to the right, and the partial pressure of ethanoic acid increased, and so on. So you can read in there, there's quite a lot of different versions in there. You can even talk about the change in Kp when the temperature changes. So there's plenty to write about, but you must have some form of reasoning in there. Again, part C, the bit that caught us up, wasn't necessarily our answer. A lot of people got the answer, but it is the word justify. So why is it the answer? So the equilibrium constant not changing, there's no effect when we add to the constant, to the value, when we add more methanol. Why? Because the only thing that changes Kp is temperature. What's happened though is in our fraction, we've added more at the bottom here. So now we've got a fraction that's bottom heavy. It's not going to equal Kp anymore. So to make sure it equals Kp, then the equilibrium moves to the right to use up that methanol and form more ethanoic acid. And as it does that, the fraction becomes back to the value that we'd be expecting, and therefore we'd get the right answer. So the yield restores the fraction by moving the equilibrium to the right. Really important there, again, justify and explaining. We did well with the next bit, state and explain the benefit to the environment, so the idea we can use lower temperatures. And obviously the environment doesn't so much come into costs and production, but the idea certainly, and most people had, was that we don't need as much energy, and if we don't need as much energy, we're burning fewer fossil fuels. So that was really good in there. Then for the next question, we need to first of all find the amount of ethanoic acid. So we can times the MR by the moles to give us the mass, and then mass divided by density, which comes from the data booklet, or as I put on the post, 1.049. There will be a few more of these bits with data book questions, and hopefully when we're back at school or very soon, I'll give you an actual copy of it. The old ones used to have a huge amount of information, the new ones much less so, that you need to look up. But the fact of the practice of using a data book will hold you in really good stead if you're doing anything scientific at university. So we will look at some of the full data booklets, and then when you come to actually doing an exam, you've got hardly anything to look up. It'll be quite easy. Part 2, how would we measure out the volumes? Obviously 2.3 is very small volume. You got 0.2 centimeters in there, so a burette would be fine, or some sort of syringe would also be workable, but not just a pipette. You're not going to get glass pipettes that measure out 2.5 centimeters. The droppers that you're thinking about as well, they're not very accurate, so those certainly wouldn't be any good. But you could have a graduated or adjustable pipette, which sometimes you use in biology and things like that, for very small amounts. Why would we need to seal the test tubes? Well, there's a lot of water vapour. You've got some chemicals that are very volatile, so they could begin to escape. We could have the alcohol getting oxidised by the air, and to make sure that you don't have any of that, we would call that a closed system. So we close the system to allow it to reach equilibrium without all that interference, the oxidation, the air, and all the other problems that are in there. Then we've got our indicator. It's a bit of a tricky one here because we haven't quite moved on to our acids, but indicator, you'd want to use phenolphthalein. Methyl orange doesn't work at those kind of pHs. Methyl orange works for strong acids, not for weak acids. So we'd want to use phenolphthalein whenever we use a weak acid, and the colour change would be from colourless to pink. Then you've got your equation, pretty straightforward, an esterification equation. And then we've got a slightly more complicated calculation to do. So in the experiment, you've got different titrations, and you've also got the titration for the amount of hydrochloric acid. Now that's really important because we need to remove or work out how much excess sodium hydroxide had been used for the hydrochloric acid catalyst. So you've got to subtract that 11.7 from the hydrochloric acid. The ethanoic acid isn't the only acid in the test tube. There's also that hydrochloric acid, and that's got to be removed as well first. That then gives you 65.4 centimetres here. So it's quite straightforward to do concentration times volume over 1,000 to give you the number of moles. The mole ratio is then nice and easy because it's 1:1, and then that will give you the number of moles of ethanol. So if I want to know how much ethyl ethanoate was there, then I've got my starting amount and I've got how much was left, so that gives me the change. And given that there was 0 ethyl ethanoate at the start, the change is how much ethyl ethanoate had been produced. So we've got our 0.2692 there. Substitute it in, most of you managed to do that really, really well, and the units cancel. The bit we've got to be careful on, concentrated hydrochloric acid would be HCl liquid, and dilute is HCl aqueous. But in both cases, there is still water present. If HCl was pure with no water present, it would be a gas. But it's got to, for it to be a liquid, certainly at room temperature, but for it to be a liquid, then it's got to be dissolved. And to tell the difference between concentrated and dilute, we talk about HCl liquid and HCl aqueous. Your choices then, you've got first test tube, esterification, addition, condensation. We had all those different answers, and most people picked up hydrolysis for the second one, which was really good. The idea that you started the reaction from either side and you'll then reduce it and then you're meeting in the middle. The idea that you keep getting the same answer, there's lots of different possibilities in there. And the idea that it's a catalyst, just simply making the reaction faster. So question 3, we've then got methyl propanoate, and we've also got some steamy, misty fumes, and we should be quite familiar with that. That's our HCl. the table, we've got to add in the values. You can see the values there, but if you look carefully, you'll see that the ester has gone up by 0.21. So if the ester's gone up by 0.21, the water must have done the same. So the water goes from 1.2, adds 0.21, and you get to 1.41. For the others, they've been reacted, so they must change and go down by minus 0.21. So you've got 0.52, and that's going to use up some of that. It's going to use up 0.21, which gives you 0.31, and the same for the methanol. It goes from 0.37, it loses that 0.21. So filling out the rice table to help us figure it all out. Multiple choice. If you write out the KCs, then you would have N2O4 over NO2 squared, and on the other side you would have N2O4 raised to a half over NO2. Now if you put 1 into that equation, then it comes out as 1 and you might get the answer A, but that really very unhelpful. If you put 2 in, then you might begin to get some answers, or 3 or any other number, it'll begin to work. And what we should find there is that the answer is B. It's the square of that. If you square this to that, then that is x squared. For the next one, increasing the factors, so we've got A over B times C. If we increase the pressure overall, then we're going to change, and what we're going to get there is no overall change on Kp. So we're changing the amounts, the fractions might change, but the actual Kp value won't change at all. So we have C. And then finally the units, we've got atmospheres over atmospheres squared, so cancel, and much like that first problem, we get atmospheres to the -1, which is B. For question 7, which of the following would decrease the yield of methane? Really important there. We have an endothermic reaction. So obviously if we increase the temperature, that's going to favour it. So we want a decrease in the temperature, which gives us A and C. And you can see in there we've got the gas on the right hand side. So the more we pressure, the more it favours the side with the least gaseous moles, which is the left. So the answer there is C. For B, which one is going to increase the value of the equilibrium constant? Well, we can get rid of those first two straight away, because pressure doesn't affect the constant. So it's got to be about temperature. If you decrease the temperature, that's going to favour the exothermic side, which in this case would be the left. So our answer is D. And then question 8, we've got an equilibrium mixture, 4 and 6, and the equilibrium mixture contains 3 moles of the product. So Kc for the reaction, well, we've got 4 and 6, so we've lost 3. So a quick rise table, 4, 6, 0, 0. So this is plus 3, this is plus 3, that must be minus 3, that must be minus 3. So you're then left with 1, 3, 3, and 3. That goes on top, so we would have 3 times 3 over 3 times 1, and so that leaves you very quickly with the answer being C. 9, we should know about oil and water, but just in case, they've dressed it up for us with density, and the density of the hexane is much lower than water, so shouldn't be that surprising. Oil floats on water. So we're looking at the 2 with hexane on top of the water, so it must be one of these 2. And then it tells us the equilibrium constant is 85. That's a really big number. So if we think about a fraction, we've got the hexane over the water, and that equals 85, which means this top number must be much bigger than the water, which tells me there's a lot in the hexane and not a lot in the water. So the answer there is A. Question 10, which will not improve the overall yield? Increasing the pressure favours the right hand side. Liquefying and removing the ammonia, well, if you remove it, it's going to push equilibrium to replace it. Increasing the temperature, well, that's the right answer, because we have an exothermic reaction, and that's going to favour the backwards, that's going to favour the endothermic side, so that's no good to us. And there at the end, recycling the unreacted nitrogen and hydrogen, well, that's only going to be good for the overall yield, because it means every time it goes back, we're going to end up with some conversion. I hope that helped any errors you had. Please go through the paper, have a look at it, be really, really careful with any mistakes in there, particularly with things like justify. Have you put the right level of detail in there? Have you actually explained yourself, or did you just put a statement? The statement obviously is no good to us at this point. If you do need any help, please get in touch. Just send me an email and I'll get back and explain it to you. And then I will speak to you tomorrow for our first revision lesson.